And we now have Denise Lanzieri. Could you go back to the main slide? Very good. The floor is yours.
Okay, so hello everybody. I'm Denise Lanzieri. I'm a second-year PhD student at the Cosmostat laboratory, and I'm working on the forecasting the power of high-order weak-lensing statistics with automatically differentiable simulation. Okay. So we know that the next generation survey like Euclid and LSST will provide very precise shear data, but what people typically do is to do cosmological parameter inference with this data by analyzing the power spectrum or the two-point statistics. But if we, for example, look at these two maps, we can see, for example, that these are two weak-lensing simulated maps of the convergence that is just defined as the projection of the map along the line of sight. We can see that in the first map there are some structures that are not visible in the second one. But if we compute the power spectrum from this map, they basically overlapped. This is because the weak-lensing is significantly non-Gaussian, but the two-point statistics is not able to capture the non-Gaussian information in the convergence map. So basically we need to use different approaches that are able to capture this non-Gaussianity. But if we have a very precise analytical model to describe the power spectrum and analyze the two-point statistics, we don't have an analytical model to describe this non-Gaussianity. And this is the reason why we need some simulation. So in the last year, some simulation-based inference technique have been proposed, but if we want to exploit this simulation in a very efficiently way, we need to access the gradients. And so what people typically do is to compute these gradients by using the final differences, the numerical differentiation. And we know that there are a lot of issues related with this kind of differentiation, because just computer approximation, because they're very unstable, because require a large number of simulation, and became impossible for more than 3 or 4 cosmological parameters simultaneously. So we are working on a different approach that is based on the automatic differentiation. Basically, we have developed a totally differentiable lensing light cone. In the TensorFlow environment, we have developed this weak gravitational lensing package. In this environment, we implemented our set of n-body simulation with a particle mesh solver. These n-body simulations have been complemented with a potential gradient descendant scheme that is in particular an additional scheme in our n-body simulation that make our simulation comparable to high-resolution simulation. And all the results are differentiable with respect to the cosmological parameters and any systematic in the simulation itself. So for example, if we consider as a first example of high-order statistics, we can consider the peak count that are just defined as the local maxima in our convergence map. And we know that we don't have an analytical model to describe these statistics, but we can do very easily with the simulation. And so for example, as a first application, we can do some feature forecast. We can compute the derivative of this peak count with respect to the cosmological parameters, and we can do that for more than 3 cosmological parameters and for any map-based statistics. And for example, use this approach to compare the constraining power of these statistics. So basically, this is just the first step. The next step will be use this simulation just to do some simulation-based inference, and this is possible because we have a totally differentiable lensing light cone. Thank you.
Thanks a lot.